Right, if all the presenters are ready, I think we'll get this session underway. So welcome everyone for attending this session. The purpose of this session is to really get a better understanding of the characteristics of ice sheets and the kind of underlying processes, and to really try and bring together these records from the marine environment and the terrestrial environment to try and kind of provide new insight about past ice sheet behavior. Now, I'd like to acknowledge the other conveners here. So we have Ruthie Halberstadt and Julia Wellner who are joining us. So please shout out to them if you have anything you'd like any issues you'd like to raise in the chat. Also, like to highlight that as well as this, so we've got two blocks for this session. We've also got e-posters as well. So I encourage you to use the virtual platform and explore all of the e-posters. And you can find those under events, going to abstracts, and then geoscience, and then you can see this session and the posters associated. Now, the structure of the session is going to be, we're going to have 4 talks, kind of back to back, without any questions, and then we're going to have a Q&A for those 4 talks. Then we'll move on to the next 4 talks and a final Q&A. So please, as people are speaking, use the chat function to put any questions you have, and we will pull those out during the Q&A. Also, just say again to the presenters, just a note that this session is being recorded. So if you have any sensitive results up there that you don't want recorded, please pause the recording while you're presenting. And I'll also just say that, yeah, when it comes to your turn for presenting, please share your screen and then we'll get things underway. So first up, I'll stop sharing now, get things underway. So first up, we have Linda Belfort. If you're happy to share your screen.
Yes.
So Linda will be presenting some sedimentary insights into subglacial hydrology. Take it away.
Yes. All right. Hi, everyone. As you said, I'm Linda Belfort. I'm a master student of Gavin Dunbar, Hugh Horgan, and Sebastian Nair at Victoria University of Wellington in New Zealand. And I will be presenting on the sub-ice shelf sedimentary event deposits, insights into subglacial hydrological systems from the CAM ice stream, West Antarctica. First of all, I'd like to apologize for my voice. I'm at home with COVID. So yeah, just getting that out of the way. I will be presenting the preliminary findings of the 2021-2022 field season in Antarctica. And for that, I'll really have to thank the Antarctic Science Platform and Antarctica New Zealand for allowing me to go down there in the first place, and to GNS Science for their collaboration on this project. All the people in this photo were with us down in Antarctica for 4 weeks. And this includes a team from Cornell University, the IceFin team, a team from NIWA, Otago University here in New Zealand, and of course our amazing engineering and drilling team at Victoria University, without whom this project wouldn't have been able to happen. So we went to the CAM ice stream, which is highlighted here in yellow and is located in the eastern Ross Sea. And we drilled at KISS 2, which is located over here, which is right at the grounding line of the West Antarctic Ice Sheet, where it starts floating and becomes the Ross Ice Shelf. Here we drilled through 500 meters of ice and collected a 53 centimeter soft sediment core from under there. This is a really unique site as it's located right at the mouth of a subglacial channel. And this is an environment that has never been physically investigated before. So I am incredibly excited to report on 3 key initial outcomes that we found, which relate to the stratigraphy, biomarkers, and diatomite class that we found in the core. So this is our core. This is the CT image. In this image, darker colors are low density, and bright colors are high density. And within here, we have found 3 event deposits. The top 2 in blue are reverse graded, and the bottom one in orange is normally graded. I need to do more grain size analysis to be able to say exactly why these top 2 are reverse graded, but it's interesting nonetheless. The top 5 or so centimeters of this core consists of a laminated mud, and the bottom 13 or so centimeters, which I've highlighted here, is roughly normally graded as well. But what's interesting in here is the low density class that we found in here. And these are these diatomite class, which I'll get into in a little bit. So why these event deposits? Remote sensing techniques have observed elevation changes in the surface of the ice sheet. And they've interpreted these as these cascading drainage event, or this filling and draining of these active lakes underneath the ice sheet. Now, when this happens, quite a lot of water gets pushed through these subglacial channels, and they can create these turbidity flows or density currents, which we are seeing in the core. So it is really good to align these theoretical observations and these indirect observations with the physical evidence that we see in the core. Kim et al. Have done a study on the Cam stream on this episodic filling and draining of the lakes. As you can see here, we're looking at the trunk of the Cam stream, and the yellow is the grounding line. And they've identified 3 lakes in there, KT1, 2, and 3. In the graph in the middle, they've observed an elevation change and the volume change of these lakes that were happening late 2013. Their modeling and the modeling of other papers have suggested that these episodic drainage events occur on yearly timescales. Because we have no age control on our core yet, we are suggesting that our core likely represents a few decades rather than a few centuries or even longer. So it's really quite exciting to see evidence of this in our core. Now, when we drilled through the ice and the NIWA team put a camera down the borehole, we found quite a lot of life under there in the form of crustaceans, which is really interesting considering that we're so far away from the open ocean. This prompted us to start doing biomarker research on our core. And because this hasn't really been done before like this in sedimentary cores from these regions, we decided to do this on a reconnaissance level, so really do a bulk analysis. Now, I need to stress, this is incredibly preliminary. We have not quantified or identified all of it yet, but I can report on a few big first impressions that we have. So the first one is that the core is full of reworked organic material, also in terms of biomarkers. And you can see that here, we've got some bacterial and algal indicators, as well as diatom indicators and bacteria. But most interesting are the higher plant signatures that are coming through in most of our samples. So since Antarctica does not have higher plants as it stands right now, we are saying that this has to have been reworked from an older time. So if you remember those low density clasts that I pointed out in the CT image, I picked those out and I cleaned them off and I imaged them with our scanning electron microscope, and they turned out to be diatomite clasts. David Harwood at UNL has looked at our diatomite clasts and has identified them as early Miocene and having an early Miocene assemblage of about 18.8 to 18 million years old. And these are the same assemblage and have the same characteristics as diatomite class found in J9, which is located further in the center of the Ross Sea. Now, interestingly, J9 is the sediments in J9 were coming from underneath Willen's ice stream, and our sediments are coming from underneath the Cam ice stream. So this diatomite deposit needs to be quite extensive, but I'll get into that a little bit more. So this is an image, an SEM image of the diatomite class, and you can see that they are full of diatoms. At the bottom right is an image that David Harwood has prepared and how he looks at the diatoms. But this is really good to show the difference in preservation state of these diatoms. Some of them are really, really broken up. Some of them are almost pristine still. And we've also found that in the SEM images, quite a big difference in how they're preserved. So this diatomite is indicative of open water during the early Miocene over a large part of where now the West Antarctic Ice Sheet lies. And if we pull that together with the signatures from the biomarkers, we're suggesting that this region of the Eastern Ross Sea region would have looked somewhat similar to what modern Patagonia looks like today. So subpolar with some shrubs and some grasses, but not a whole lot of vegetation. So Miocene diatoms are very common in quaternary sediments derived from West Antarctica, but this does imply that somewhere underneath the West Antarctic ice sheet has to be the source of this material. Since there are now outcrops of Miocene diatomite anywhere along this region, we can conclude that they must be somewhere underneath the West Antarctic ice sheet, and so they must be outcropping somewhere underneath the West Antarctic ice sheet. Horgan et al. Have done a seismic line across the Cam ice stream grounding zone. And they found this quite bright reflector horizon D, which is shown in the bottom image. Everything above horizon D has been looked at, and no in situ diatomite has been found there. So we suspect that the diatomite must be lying below this, and then, as I said, outcropping somewhere underneath the West Antarctic ice sheet. Now, this is completely speculative, but the source must be somewhere underneath both the Cam ice stream and the Willens ice stream, as they've been also found at J9. And there must be quite a lot of it, since these reworked diatoms are found all over the Eastern Ross Sea. And the seismic character of horizon D does suggest more indurated sediments, which is consistent with these diatomites. So in summary, the core stratigraphy supports the notion of short-lived, high-velocity discharge events in the Cam and presumably other sub-ice stream drainage systems. And the microfossils and the biomarkers are dominated by material reworked from the mid to early Miocene, and they suggest a subpolar climate with open water conditions where waste now lies. I would like to add that we are also trying to get a temperature indication from these diatomite clasts through biomarker research. So that's currently happening, and more grain size and XRFing is going to be conducted on the core. Thank you so much.
Great, thanks, Linda. That's a great start to the session, I think, and especially well done considering you're currently ill, so well done.
Thank you.
So if the next presenter would like to share their screen. So as I said before, we're going to do a Q&A session after 4 talks. So please post any questions in the chat and we will come back to those. So next up is Jessica Gagliardi. You can share your screen. We'll be talking about subglacial precipitate record and kind of millennial scale changes.
Okay, are you guys seeing it's not in presenter view?
Looking good from our end.
Okay, awesome, great. Hi everyone, thank you all for being here. My name is Jessica. I'm a PhD student at the University of California, Santa Cruz. My advisor is Terry Blackburn, and I'm here to talk to you guys about Antarctic subglacial precipitates and how they show the ice sheet responding to Southern Ocean warming. So before I get into it, I just wanted to thank my collaborators at UCSC, Terry Blackburn and Slavik Tulacic, who have advised me on this project, as well as my fellow grad student, Gavin Piccione, who's going to be talking to you about some of his work with precipitates in a little bit. I also wanted to thank everyone who provided us with samples, and a special thanks to Anne Grunau at the Polar Rock Repository, who is going to be presenting tomorrow. And then also to John Stone and Christine Sidaway, who provided samples to us as well. And then finally, a thank you to the NSF for providing the funding for this project. So the motivation for this work is that we know, based on offshore sediment records, that the Antarctic ice sheet advances and retreats in response to these 100,000-year climate cycles that arise from changes in the shape of Earth's orbit called Milankovitch cycle. And so as you can see in the figure here, where we have time on the x-axis and the delta deuterium record from the Epic Dome Sea ice core, which is a temperature proxy on the y-axis, you can see the peaks in this blue line happening about every 100,000 years. But what we're interested in is how does the ice sheet respond to suborbital millennial climate cycles? And so we're going to look at these millennial scale warm periods called Antarctic isotope maxima, which are the red dots on these smaller temperature peaks that you can see here on the temperature record. So what causes these suborbital climate cycles? The short answer is ocean circulation. So one of the arms of the global thermohaline circulation system is the Atlantic Meridional Overturning Circulation, or AMOC, which is an ocean current that transports heat south to north. But AMOC's strength and efficiency with which it transports the heat is variable in time for reasons that we don't have time to get into today. But the result is that during periods where AMOC is strong and transporting heat more rapidly, the Southern Ocean cools and the North Atlantic warms. But during periods where AMOC is weak or shut off, the Southern Ocean warms and the North Atlantic cools. This causes a temperature offset between the North and Southern hemisphere called the polar seesaw, which you can see here in the figure on the right, which is showing a period from 30 to 60,000 years ago on the x-axis. And then on the y-axis, down here at the bottom, we have 3 different temperature proxies from the Southern hemisphere. And then up here is a temperature proxy from the Northern hemisphere. And they show this offset between the Northern and Southern hemisphere. That is the polar seesaw. And so the oscillations in AMOC strength cause climate oscillations in both hemispheres, as you can also see on this graph. And that's where these AIMs are coming from. So the peak of an AIM here is occurring when AMOC is weak or shut off, and then the trough is occurring when AMOC is strong. So now I'm going to shift a little bit and talk about the samples that we used in this study to investigate how the ice sheet is responding to these changes in climate. So the samples we're looking at in the study are calcite precipitates that form in aqueous subglacial environments. And I'm calling them new climate archives because they haven't really been used to study ice sheet histories in this way before. And so I have some sample photos here on the right that show the wide variety of textures and morphologies that we see in these samples, which were collected at different locations during various Antarctic field seasons. So they're found across Antarctica. The ones that I worked with in this study were primarily these single layer crusts, but there are more in our sort of overall collection of data that Gavin's going to talk to you more about later that are these alternating layers. But the ones that I've dated as part of my work are these single layer crusts, for the most part, that you can see here on the right. And so they're found across Antarctica. The most important thing to note about these precipitates is that they can only form in the presence of water. And so their existence tells us that there has to have been water in the place and time where they formed. And we can measure their ages in our lab using U-series dating. So that's what we've done for this project. So these samples are found at locations near the margins of the ice sheet and along the transantarctic mountains, which you can see are the yellow circles are all the different sample locations. And what's important to note about this is that these are also the areas of the ice sheet that we expect to be cold-based or frozen to the bed, while the more interior regions are wet-based and will have water at the bed. But as I mentioned, calcite precipitates can only form in the presence of water. So this sets up the question of how do we explain the presence of the water that formed these calcites that are found at the margins of the ice sheet in regions where we don't expect to find liquid water at the bed of the ice sheet? And so what we're going to try to do is to correlate the ages of these calcites with the AIMs, the Antarctic isotope maxima, which again are the millennial scale warm periods. So what we've done here is we've plotted the ages of the calcite, which are shown in yellow, alongside the delta deuterium record in blue, at the AIMs pointed out on the delta deuterium temperature record in the red circles. And so the ages plotted here are a compilation of the single layer calcite crusts that I dated, the layered calcites that you're going to hear about later from Gavin, and a few previously reported ages. And so when we plotted these things together, we made the first order observation that the calcite ages do appear to be correlated with the AIMS. But in order to test whether this correlation was statistically significant, we used a Monte Carlo model to test how likely a randomly generated distribution of ages was to show the same level of correlation as our ages. So to do this, we generated an artificial data set of random ages and then summed the residuals between each artificial age and its nearest AIM, which you can just think of as a measure of how close the ages are to their nearest AIM across the whole data set. We then repeated that for 10,000 different randomly generated data sets, and that's what's shown in this histogram here. And then this black bar shows the sum of the residuals for our actual data set, which you can see falls well outside of the 95% confidence interval. So that establishes that the ages that we measured are not randomly distributed, and there is statistical significance to their apparent correlation with AIMS. So a random distribution can't recreate the same level of correlation as our data set. And so now that we can say that the calcites are correlated to the AIMS in a statistically significant way, we need a mechanism to explain how they are connected. And so I'm just going to quickly run through the working model that we have to explain the connection, but you'll hear about it in some more detail from Gavin later as well. So the question is, where do the precipitate forming waters come from? And so the conceptual model that we're working with is that an AIM event occurs, there's this warm period in the Southern Ocean, or there's a warm period in the temperature record. And that AIM causes westerlies to shift poleward. And then the shifting of the westerlies poleward causes an increase in upwelling in the Southern Ocean, which you can see in this figure to the right. We have these three different temperature proxies up here, like CO2 and delta OIT and various things. And then down here is opal flux, which is a proxy for upwelling of the Southern Ocean. And you can see this stack is establishing this correlation between the AIMS and the increase in Southern Ocean upwelling. Ocean warming then causes grounding line migration and ice surging. So you can see in this schematic sort of the upwelling of the warm water from the circumpolar deep water. And then it's kind of undercutting the ice sheet, causing the grounding line to migrate. And then that in turn causes ice surging at the outlet glaciers. And the ice surging leads to basal shear heating, which generates enough water at the base in these otherwise cold-based regions to activate the subglacial hydrologic system, which then leads to the flushing of interior waters. And that's what's able to precipitate the calcite out in these otherwise cold-based regions, is waters from the interior of the ice sheet flushing out to the edges being activated from the basal shear heating. And so that's our working conceptual model for how we connect the presence of these calcites to the AIMS, which is this atmospheric temperature event, is these teleconnections between the atmosphere to the ocean, to the ice sheet, to the subglacial hydrology. And so in summary of everything we've talked about here today, we dated single layer calcite precipitates from Antarctica with U-series dating. We observed a correlation between the calcite ages in Antarctic isotope maxima, and then we further tested that correlation with the Monte Carlo model. And our working model of ocean forcing to grounding line migration to ice surging, which then causes basal shear heating and flushing of interior waters, is kind of our explanation for the teleconnections to get from the AIMS to the calcites. And so that's all I have for you, and thank you.
Great, thanks, Jessica. Really interesting talk. If the next speaker can share their screen. It's you, Alex. So again, everyone, if you've got some questions, please chuck those in the chat and we'll come back to those in the Q&A. So up next we have Alex Sims talking about relative sea level in the Antarctic Peninsula. Take it away.
Great. Can you hear me now?
Yep.
Okay, excellent. Well, thanks everyone for giving me a few minutes of your time. I'm going to be talking about a very different time scale, sort of the Holocene, last glacial maximum to the present, compared to a couple of the other talks we've heard already. So before I get started, I'd like to acknowledge a couple co-authors on this, a couple former students, Cameron, Julie, and Brittany, as well as a colleague at East Carolina, Regina DeWitt, and her PhD student, Chris Garcia. So over the last, several decades, we've learned a lot about Antarctica. And there are two things that I wanted to point out that are important for my work here on the Antarctic Peninsula and for this talk. The first is that the Earth's rheology beneath portions of West Antarctica and the Antarctic Peninsula is relatively weak. And what I mean by weak is that it has a relatively thin lithosphere, 30 to 50 kilometers, and low upper mantle viscosities on the order of 10 to the 18th to 10 to the 19th pascals per second. And why is this important? Well, that means with such, a weak Earth beneath this parts of Antarctica, that means that its potential to be very responsive to sort of small scale oscillations in the ice sheets. So the second thing that we've kind of learned that is important for my talk today is that you can see Richard's recent paper here kind of gives us an overview of some of these Holocene oscillations in the ice front at some locations. So we can see here, this is thousands of years ago, and this is sort of mass loss from Antarctica. And during the early Holocene, we can see that there are periods where we had accelerated ice loss from Antarctica. And what's important for me in this talk is what's happening during the late Holocene. And you can see not only are there periods where you had more or less mass loss, but there are actual periods of mass gain or ice advance during the Holocene. So what we're interested in is, does relative sea level data across Antarctica record, or at least within the Antarctic Peninsula, some of these oscillations in the ice front? Now, the first thing to kind of think about is that, since the last glacial maximum 20,000 years ago was the height, but in Antarctica, it's, the ice was, large till, 10, 12,000 years ago. But because Antarctica contained ice, as that ice melted, it rebounded quicker than sea level globally rose. And as a result, we generally get the curve shown here on the upper right, which is this exponential decrease in sea level fall throughout the Holocene. Well, one thing that we have noticed as we start to get better records of relative sea level changes across Antarctica is there are actually periods of accelerated fall, not just this exponential decrease in the rate of sea level fall. And that can be shown here in the lower diagram, where we have relative sea level change here, up being fall, down being rise, back through time, back to 3,500 years ago. And we can see in this case, 1,500 years ago, there was an acceleration in the rate of sea level fall. And we think that those are being driven by accelerated retreat of the ice. So the question I want to ask is, we see these records of accelerated sea level fall preserved during the Holocene. What about minor RSL rises? We know that there are advances during the Holocene, and here's a little ice age moraine from the Antarctic Peninsula. Are they reflected in the relative sea level history from Antarctica? And so in theory, these advances, minor advances, might be enough to cause minor relative sea level rises or still stands during the overall RSL fall following the last glacial maximum. So how might this RSL rise be recorded? Well, most relative sea level data from across Antarctica comes from raised beaches, like this set of raised beaches here on Joinville Island. There are some isolation basins, but they're few and far between. Unlike more temperate locations, there are no marshes in Antarctica, which is unfortunate because marshes provide really high resolution records of past sea level. So that leaves us with these raised beaches, but the rises may be buried beneath those deposits. So how do we look at the subsurface of these raised beach deposits? We decided to look at ground penetrating radar profiles, or GPR profiles. And I'm going to show you data today from Livingston Island here at the northern tip of the Antarctic Peninsula. So here's our study area. This is the tip of the Antarctic Peninsula. This Livingston Island is within the South Shetland Islands. I'm going to refer to Joinville Island in my talk as well, and that's where it is located here. We collected about 10 kilometers of data from Livingston Island. The red lines show where our data was collected in this part of Livingston Island. We used a 200 megahertz antenna that kind of gave us a good sort of balance between depth of penetration and the resolution that we were able to image within our GPR. So what might we be looking for in case of a transgression or a relative sea level rise? Well, assuming sediment supply isn't crazy, a relative sea level rise would likely cause a transgression within the coast. And during transgression, we often get a shoreline shift or a landward shift of the shoreline, which results in erosion at the coast and onlap of deposits a little more seaward. And so those are some things that we can look for buried within these deposits, maybe erosion, coastal erosion, and that onlap. So we collected a bunch of GPR. We saw, as good stratigraphers, we identified several facies, GPR facies. The two that are important for my talk here today are these seaward dipping reflections, which just represent the progradation of the coast as sea level is falling, and these landward dipping reflections, which represent sort of overwash, largely from maybe storms and so forth. We found a number of radar surfaces. The one that I'm going to focus on today is what we're interpreting as the base of the Holocene, or the top of the bedrock. And these are hyperbolas and ringing below with downlap above. And one of the things that we think we found, and I'll show you that here in just a second, are these prominent erosional scarps. So here's what the GPR data looks like. This over here to your right is landward, to your left is seaward. It's hard to tell, but between the bottom and the top, we have about 12 meters of elevation. And what we can see here as we go from right to left, we see this sort of seaward dipping reflections that represent that progradation of the coast as sea levels falling. But it's interrupted by these very big or abrupt sort of scarps here, or really high beach ridges. And the magnitude of this fall here is about, or relief here is upwards of 4 meters. If we zoom in on these sort of prominent beach ridges, they all have a very similar architecture beneath them, in that we see sort of seaward dipping reflections. To your left is seaward in this case. And then when we get to the beach ridge, we actually see landward dipping reflections. And immediately beneath it, we see a scarp in the bedrock right here with onlap. And it's not just here, it's in underneath every one of these high beach ridges that we've imaged. Here, seaward is to the right instead of to the left. And we can see that scarp and the landward dipping reflections on top of it. We compiled ages, already existing radiocarbon ages from these beach ridges, and they date to about 400 years ago, 1800 years ago, and 5,500 years ago. Now, one thing I was worried about is, are these scarps real, or are they just where we're getting sort of loss of penetration beneath that sort of abrupt break? But within stream cuts, we have a GPR profile right across here where we see that same thing. And this is oceanward. back this way is this is seaward and this is landward. We can see that those scarps are real. We can see them in outcrops from these sort of stream cuts through these beach ridges. So what causes these natural breaks in the scarps? A couple possibilities. One is Livingston Island is overlying a trench, a subduction zone. So we might expect coseismic uplift. However, that would not explain a couple things. One is where we do have these prominent beach ridges, we see these sort of incipient ridges developed on them. If it was a single event, we would see beach ridges above and beach ridges below, but nothing in between. It also would not explain the scarps buried beneath these beach ridges. The pattern of uplift sort of fits more glacial isostatic adjustment. This might work for the South Shetland Islands, but we see the same pattern on Joinville Island, which is not overlying a subduction zone. So what we suggest is that these are caused, this morphology, this geometry to the deposits is caused by oscillations in sea level, which are driven by changes in the ice sheets. And so this is our model over here. This is the ice sheet. This is the stratigraphy that's developed. So from the LGM, the ice retreated, so sea level fell, and we get these sort of seaward dipping reflections. The ice advances, that depresses the crust, which causes sea level to rise. We get erosion, the creation of the scarps. The deeper water brought closer to shore allows overwash to be preserved. The ice then retreats. We get accelerated sea level fall and the draping of those scarps with beach deposits, and then it continues as we still see the relaxation from the LGM. And then it repeats again during the next oscillation. And so what we see, instead of this exponential decrease in the rate of sea level fall, it's interrupted by these minor transgressions during the Holocene. The most recent of these beach ridges dates to the Little Ice Age. So in summary, GPR profiles and stream cuts show distinct steps in the bedrock beneath prominent anomalously high beach ridges. We hypothesize that these scarps and erosion represent minor RSO rise. The youngest of these dates to Little Ice Age. There were two others at 1.8 and possibly 5.4 thousand years ago. And these oscillations may complicate what we're able to derive from the inversion of sea level data if we assume that it's only a unidirectional ice sheet. So I'd like to thank the National Science Foundation for funding this work, the captain crews of a couple boats that allowed us to get there and more importantly, get back from Antarctica. And some other people helped us in the field as well as with the radiocarbon data. Thanks.
Great, thanks, Alex. Really nice talk. Lots to discuss there, but we will save some of that for the Q&A. And so again, please put any questions in the Q&A or in the chat as people are giving talks. Next up, we have Kerry Rand, if you're happy to share your screen. So Kerry will be talking about past ice thickness change in East Antarctica. Take it away.
Sorry, I was muted, unmuting. Everybody can see my screen? Okay.
Yep, all good.
Hi, my name is Kerry Rand. I'm a student at Monash University in Melbourne, Australia, working on my PhD in geology with my advisors, Drs. Jones and McIntosh. I am also being assisted by Dr. Gehring from Tulane University, and we're building on some work done by Dr. Lilly, currently at University of Otago. So I'm here today to talk about some work in which we've been investigating the post-LGM ice surface elevation history of a non-coastal area of East Antarctica using in situ cosmogenic radiocarbon. So it can be tough to measure paleo ice surface elevations in Antarctica due to the continent's remoteness and inhospitality. This is especially true in East Antarctica because the majority of the rocks on that half of the continent are currently mantled with ice and have been for some time. The majority of the direct measurements of past ice surface elevations in East Antarctica come from coastal regions, both because those regions are the easiest to access and because they have the most outcropping rock. Ice surface elevations can be reconstructed from deep ice cores, which are often sited close to ice divides. What evidence we do have points towards unchanged or decreased ice surface elevations in the East Antarctic interior at the LGM. Many estimates of interior sites as ice surface elevations are derived from ice sheet models and ice core records, such as those from Dome Fuji or Epica Dome C here, as exposed nunataks are few and far between in the continental interior. Non-coastal rocks exposed above the ice sheet surface are valuable as constraints on the ice sheet surface elevation between core dome sites. Cosmogenic exposure dating at these sites is in apparent agreement with ice core-based reconstructions, showing little evidence of thicker ice at the LGM. In contrast to the interior, cosmogenic exposure data from locations in coastal East Antarctica often indicate LGM ice surfaces situated up to hundreds of meters above their present elevations, both right along the coast, as in the Brown Range of McRobertson Land, and in the Prince Charles Mountains along Lambert Glacier. Our study site is the Grove Mountains, situated roughly 500 kilometers south of the Antarctic coastline and roughly 200 kilometers east of Lambert Glacier, into which ice flowing through them drains on its way out to the sea. Current ice sheet surface elevations in the area are roughly 1,800 meters above sea level, and the nunataks as summits rise a couple hundred meters above the ice on average. Few other nunataks are exposed for hundreds of kilometers in any direction. Samples were collected in the transects stretching from the ice's surface up the ridge of a nunatak to just below its summit. A cross-section of this transect is shown here. We used in situ cosmogenic radiocarbon concentrations from these samples to calculate our paleo ice sheet elevations at the site. Previous work at the site examining cosmogenic aluminum-26 and beryllium-10 suggested no LGM thickening. In situ cosmogenic nuclides are nuclides produced by the interaction of high-energy cosmic rays or their spallation products with atoms within mineral grains. These nuclides accumulate within mineral grains, in this case quartz ones, while those rocks are within a certain mass depth of the surface, as in while they're not buried too deeply. Thus, as an ice sheet surface lowers, the slope will be gradually exposed. Rock at higher elevations will be exposed first, and thus will have accumulated nuclides for longer than rock at lower elevations will have, leading nuclide concentrations to increase with altitude. Cosmogenic radionuclides are important chronometers due to the combination of production of nuclides by cosmic rays and loss by radioactive decay. When the production of new nuclides is balanced by decay, the concentration of a rock surface reaches what's known as saturation. Our model of this is as follows. We start with an exposed rock sample as represented by the trapezoid shown here. Cosmogenic nuclides accumulate in the exposed rock. If the rock is then buried by ice, the nuclide accumulation rate is decreased. If the sample is buried deeply enough, production can be effectively cut off. Radionuclide concentrations in the sample begin to fall as radioactive decay begins to outweigh the reduced production rate. The concentration falls until it reaches the new saturation concentration, at which point loss to decay is again balanced exactly by production. Were the rock then re-exposed, the radionuclide concentrations would then increase again, increasing back to the surface saturation concentration. Thus, a sample must be buried for a sufficient length of time in order to reset its clock. While a saturated sample only allows us to calculate the minimum length of time for which it may have been exposed, it also, therefore, tells us that any episode of burial experienced by the sample must have occurred so briefly or so long ago that concentrations within the sample have had time to return to saturation, which, combined with knowledge of the general glacial history of a region, allows one to make interpretations about the glacial history at that sample's specific site. This has important implications for East Antarctica especially, as we'll touch on momentarily. Before that, however, it's important to note that a great deal of East Antarctic cosmogenic exposure literature is based on work analyzing long-lived radionuclides such as aluminum-26 and beryllium-10, which have half-lives of hundreds of thousands to millions of years. These long half-lives mean that concentrations of these samples will increase very slowly during periods of cover, decrease very slowly during periods of cover, meaning that inventories of them in a sample have the potential to contain inheritance, or nuclides present in a sample which were produced not during the present or last period of exposure, but sometime before the previous period of burial. Inheritance can complicate the interpretation of cosmogenic nuclide concentrations, as it makes it difficult to confidently state when a sample was last reset. This is especially true in East Antarctica, where low erosion rates mean that samples with sometimes tens of millions of years of exposure may retain much of their long-lived nuclide inventories even after a full glacial period. Due to its short half-life, in situ radiocarbon is, therefore, a very useful tool for studying specifically post-LGM glacial histories. Imagine, for example, that we have a sample which has been exposed long enough to become completely saturated with both radiocarbon and beryllium-10. If we imagine that the sample was buried 40,000 years ago and remained covered for 25,000 years, the majority of its radiocarbon inventory would have decayed away. The beryllium-10 concentration would still likely be within instrumental uncertainty of saturation. Thus, based only on its beryllium-10 concentration, we can say very little about the post-LGM history of the sample, but based on its radiocarbon concentration, we'd be able to confidently state that the sample was covered. The last glacial period was thus lengthy enough to effectively reset the radiocarbon concentrations of buried rock, and it didn't end long enough ago in East Antarctica for samples exposed only after the LGM to have reached saturation again. Thus, finding a radiocarbon saturated sample there indicates that the site from which it was collected was exposed even at the LGM. Conversely, a radiocarbon unsaturated sample would indicate that its location was covered at the LGM, and the concentration of such a sample can be used to calculate the net exposure duration of that location since the LGM. None of this is to say that longer-lived nuclide data is incorrect or even misleading. The thing to remember is simply that the nuclide concentration of the sample indicates its net exposure since it was last reset. For long-lived nuclides, that reset was millions of years ago. Radiocarbon, on the other hand, was reset by the last glaciation, so it only tells us what happened since the LGM. We can thus construct a post-LGM glacial history from a plot of samples as elevations and concentrations. This is such a plot on which our samples, shown as blue circles, appear with their elevations on the y-axis and in situ radiocarbon concentrations and uncertainties on the x-axis. Overlain on this graph are exposure isochrons, illustrating the net exposure duration of each sample. On the left is a gray band indicating the uncertainty window of saturation. Any sample plotting within this band is saturated with in situ radiocarbon, meaning we can determine only a minimum exposure duration for it. The location of the LGM can thus be inferred here to have been between the highest elevation unsaturated sample and lowest elevation saturated sample, between 1894 and 1912 meters above sea level, 100 or so meters below the summit of the Nunatak. This plot here shows the elevations and calculated exposure durations of each of our unsaturated samples, with lines drawn between adjacent erratic samples. The slope of the line between samples on this kind of plot shows the average rate of ice surface lowering at the site. Assuming a simple lowering history, this data would indicate approximately 5 millimeters of lowering per year, with rates increasing in the last 5,000 years. Additionally, we can infer from the calculated exposure duration of our highest elevation unsaturated sample that deglaciation had begun here by approximately 14.8 thousand years ago. And from that of our lowest elevation sample, the ice surface had reached its current elevation by approximately 1.3 thousand years ago. Further demonstrating the value of in situ radiocarbon for post-LGM applications, past work on these same samples measuring aluminum-26 and beryllium-10 concentrations indicated tens of thousands of years of exposure at minimum. A similar pattern has been observed in West Antarctica, where sites that exhibit only pre-LGM beryllium-10 or aluminum-26 ages, indicating no LGM thickening, do show post-LGM in situ radiocarbon ages. Furthermore, the deglaciation chronology here fits the Grove Mountains into a broader deglacial history of the Lambert Glacier. Cosmogenic exposure ages of terrestrial samples from the Prince Charles Mountains and radiocarbon dating sediment cores in Prince Bay show deglaciation initiation ages from 15 to just under 14,000 years ago to the south, decreasing in age both northward and towards the glacier by several thousand years. This has implications for modeling of the East Antarctic Ice Sheet, as many models depict only negligible thickening, if any, for regions of the ice sheet this distant from the coast. There are two possible interpretations to this. If the LGM thickening inferred at the Grove Mountains occurred across interior areas of the ice sheet, the results of simulations that don't model this behavior could diverge significantly from the actual glacial history of the region. This could affect more than just modeled interior regions. Modeled glacial flow downstream of the continental interior would also be affected were a volume of additional ice in the upper catchment unaccounted for in the model. Alternatively, models which predict thickening at the coast of eastern Antarctica but not in its interior may be underestimating the distance inland over which the coastal glacial regime is dominant. Regardless of which scenario is correct, these results can also serve as additional data for glacial isostatic adjustment models, which rely on constraints of the volume and distribution of ice to accurately model geodetic uplift. If the thickened LGM ice sheet was in fact widespread across East Antarctica, it could also tell us something about the source of meltwater pulse 1A. Although our data indicate only about 20 meters of ice surface lowering during the meltwater pulse and up to a similar amount sometime between then and the LGM, if that thickness was lost over the entire area of Central East Antarctica, it could represent on the order of tens of thousands of cubic kilometers of ice. However, this could account for less than 1% of the measured post-LGM rise in global sea levels. Additional samples in the region of the LGM limit at this site would allow us to further constrain the exact elevation of the LGM ice sheet, allowing us to more precisely gauge the amount of ice surface lowering in the immediate lead up to meltwater pulse 1A. In situ radiocarbon dates from the other exposed areas in the East Antarctica, the East Antarctic interior, would go a long way towards answering the questions posed by our data. However, the unfortunate reality is that there's only a limited number of exposed sites in the East Antarctic interior. Purple areas on this map represent rocky areas currently exposed above the ice sheet and are, as can be seen here, notably absent across much of the interior. We have plans to measure radiocarbon from locations in Accidental Valley in the southern Prince Charles Mountains on the east side of Lambert Glacier and Mount Lanyon on the northern Prince Charles Mountains on the west side of Lambert Glacier. This will hopefully allow us to more accurately constrain the timing with which deglaciation was initiated and rate with which it proceeded through the Lambert-Amory system. To summarize, caution must always be exercised when interpreting long-lived cosmogenic nuclide data in Antarctica, as Antarctic samples can contain significant concentrations of inherited nuclides. Cosmogenic exposure ranges and low erosion settings should always be checked for potential inheritance. For questions about post-LGM glacial behavior, in situ radiocarbon allows us to sidestep the issue of inheritance, as it decays quickly enough that surface concentrations could be reset by blast glaciation. For questions that reach further back in time, longer-lived nuclides may be more appropriate. Concentrations of in situ radiocarbon measured in samples from a site in inland East Antarctica now show clear evidence that the ice sheet was thicker at the LGM than it is now. The East Antarctic ice sheet, therefore, may have been thicker across its interior at the LGM, or coastal thickening may have extended further inland than current models predict. Thank you.
Great, thanks, Terry. Now, let's take it to the Q&A. And so please jot down any questions you have, and we will read them out for the presenters. So if I'm looking at this, the first up, we have a question for Jessica. Great presentation. Are there any other evidence of calcite dissolution at later stages of the AIM events?
Yeah, these are great questions. Thank you. So we have thin sections and SEM data for some, but not all of the samples in this data set. And we've never seen any evidence of calcite dissolution. We have seen on some of the crust that I didn't have time to talk about this today, but I have some very cool samples where we have a bunch of different samples from one location in an outlet glacier in the Ross Sea, where we've seen opal deposited, like a very thin layer of opal deposited on top of some of the calcite, like right on top of it, and so there's no evidence of dissolution there. And then the second question, any correlation showing the data calcite leading or lagging? So we don't have the resolution on the AIMs to show if it's leading or lagging the AIM events. So the short answer is we can't tell. But the suite of samples that I just mentioned in the outlet glacier on the Ross Sea is showing, I didn't have time to talk about this today, but it's showing some cool preliminary results that these calcite crusts can also be associated with terminations. So they're all dated to during the last glacial termination. And they do appear on a very preliminary level to possibly be leading the termination relative to, say, like the cosmogenic data that's in the area by several thousand years. So with the termination that's more recent, we are able to get a little more resolution, and it shows a little bit of leading the termination. So yeah, thank you for the questions.
Thank you for the answer. Got a question here for Alex. Could you explain the process for localized erosion to form the scarps during transgression?
Yeah, can I share my screen to answer that? Is that okay?
Yeah, go ahead.
Great. So thanks for the question. Terry, hopefully you can see this. Can you see this, hopefully?
Yep.
Okay, excellent. So the question is how explain the kind of process on why a sea level rise or transgression would cause erosion. And this kind of gets back to something that, maybe works, maybe doesn't. There's sort of this thing called the Bruin rule, which is the coastline kind of has this sort of equilibrium. And it reaches sort of this equilibrium profile shown, I guess, this is for sea level fall. For sea level rise, you can imagine here's that equilibrium profile. As sea level rises, you shift that inland, and where that will basically erode the material in between the two sort of equilibrium profiles. So right here, you kind of get the deposition of stuff, but behind that profile, you get the deposition. Out here, you get erosion, and that gives you that profile. If you shift that profile up and landward, it ends up in erosion. And then that's why, many coastlines today where sea level is rising, we get sort of beach erosion. I hope that answers that question. So, okay, great.
Looks like it does, yeah.
Okay, and then the second one, I think, was Pippa.
Yes.
Is it okay if I just jump to that while I'm here?
Yeah, I'll just read it out so everyone's on the same page. So Pippa asks, how would storm events be recorded in the stratigraphy?
Yeah, great question. Thank you, Pippa. I mentioned that we saw a couple other different surfaces besides the one that I pointed out, which was sort of the top of the bedrock. And if you can see these little red lines here, these are minor erosional surfaces. And based on work from other margins and so forth, that have actually sort of observed these in modern sort of conditions, when a storm comes across, they see one of these sort of form. We're interpreting those as our storms. So definitely they do create erosion, but they're not at the same scale as these scarps that we're sort of seeing here in our profiles and interpreting as a minor relative sea level rise. So I hope that helped.
Great, thanks, Alex. We got another question here from Julia for Linda. What do you mean by event bed, especially for the reverse graded bed? What sort of event do you think made those beds, and what is the evidence?
So when these lakes drain, they release quite a lot of water in quite a short amount of time. Or at least that's what we think. These event beds are probably sandy debris flows or turbidity flows, but the grain size data isn't, like, I haven't got detailed enough grain size data to definitely distinguish between the two. And because the mechanism for creating reverse graded beds is different between sandy debris flows and turbidity flows, I can't for certain say what happened. It could potentially be that the energy of the flow changed during the flood, because these lakes have also been shown to have to kind of overcome a barrier before they start draining. So maybe that has to do with it. It can also have to do with the dispersive pressure between the grains if it's a sandy debris flow. But again, I need to do more detailed grain size analysis before I can actually answer this. Yeah.
Great, thank you. We've got any more questions? Feel free to use the Q&A. I've got one for Jessica. Perhaps it was just me, but I wondered if you could clarify the mechanism regarding the warm water grounding line migration and then glacier surging. I wasn't entirely sure that link and how it led to the water that you're recording in the precipitates.
Yeah, so I think it's essentially a function of like glacier mass balance is my understanding, that as the grounding line is receding, there's the ice starts to surge in response to like just as a function of mass balance, in response to like losing mass at the outlet. And I know like a lot of our thinking on this came from the papers by Nick Gollage, kind of modeling these periods of ice surging like in response to the warm period. So I think, is that helpful?
Yeah, I was just wondering, in terms of the surging, was that you're referring to kind of the ice streams or the kind of terrestrial kind of lobes? Because your records are from those kind of ice-free areas, right? Not necessarily adjacent to the ice stream, but perhaps you can clear that up for me.
Yeah. So yeah, our precipitates are collected mostly in ice-free areas, but we think that like so they come from areas that like they were under the ice and they're brought up to the surface. And so yeah, we find them in ice-free areas, but that's not like where they like originate necessarily. And I think that like I'm trying to think of like how to explain this, that the ice surging is like like causing, like, I'm not explaining this very well, but like as the grounding line recedes, essentially it's like a function of mass balance and like speeding up. And also I think that Gavin might get into this a little. He's going to go into the mechanism in a little bit more detail when he talks about this.
Okay, thank you.
Yeah, sorry.
Okay. Oh, Ruthie also just asked whether ice thickening, perhaps from warmer temperatures, more precipitation, could lead to meltwater production. And perhaps that's a mechanism in addition to or instead of the ice surging. But perhaps we can continue that discussion with Gavin's talk.
Yes, that is a great question. And I will just say that this is sort of a preliminary working model that we have, and that we're going to, as kind of like a next step going forward, we're going to be doing some more actual ice modeling to kind of test some of these different working theories that we have for how this meltwater could be generated. And so yeah, I'm looking forward to kind of addressing that in the next modeling stages of the project.
Great. Well, it's an exciting project, so looking forward to seeing more. I've got one more question, if that's all right, for Alex. So in terms of your kind of record of these kind of relative sea level oscillations, to what extent do you have an idea of, I guess, whether this is a local or kind of regional signal?
Yeah, I think it's for sure it's across the entire South Shetland Islands, so on the scale of 100 kilometers or so, and I would say regional scale. So I think throughout the Antarctic Peninsula, we see breaks that date to the same time in Joinville Island, which is kind of across the Bransfield Strait from there. We do see breaks down in Marguerite Bay, although the timing isn't as well constrained. The available dates suggest they could be at the same time. We just can't falsify that hypothesis that they're at the same time. So I would say regional. So.
Thank you. Okay, thanks for all your questions and answers. We're now going to move on to the next group of 4 talks. So Andrea, if you're happy to share your screen.
Yep. Hi, can you hear me?
Yes, we can.
Okay, okay. Sharing my screen. Okay. Can you see the presentation?
Yep, looking good.
Okay, perfect. Thank you for the introduction and good time zone to everyone. I'm Andrea, a PhD student at the University of Trieste, and I'm going to present the preliminary results of 5 sediment cores that I'm studying in the frame of my PhD project. The aim of this work is to reconstruct the evolution of the West Antarctic ice sheet during the late Quaternary, studying a transect of 5 gravity cores collected in the Glomar Challenger during the 11th and the 14th PNRA expeditions, and the analysis supported by the Antipode project. Okay. This is a bathymetric map of the Ross Sea, and here you can see highlighted by the red rectangle the study area and the location of the 5 gravity cores that have been collected from the inner continental shelf close to the actual Ross Sea shelf to the continental shelf break. Another set of gravity cores have been previously studied by Bart and Coney, and according to their work, the West Antarctic ice sheet advanced across the eastern Ross Sea and reached the middle shelf around 27.5 kiloyears before present. And then, shortly after the retreat, the open marine sedimentation started. This is another map of the Ross Sea showing the different position of the grounding line This is the LGM in both the Western and Eastern Ross Sea. And then after the LGM, the ice sheet experienced a backstepping retreat with different timing and mechanisms because of the different morphologies of the two parts of the Ross Sea. The Western is characterized by deep and narrow basins surrounded by high relief banks, while the Eastern Ross Sea is characterized by wide and shallow basins and unconsolidated Pleistocene sediments. And these characteristics may have led to an early retreat in the Eastern Ross Sea, but the timing of the events are still debated, and this because the dates have mainly been obtained from organic matter, which is aged in Antarctica and also is less reliable than calcium carbonate. So studying this site is fundamental to better reconstruct and to constrain the evolution of the ice sheet since the last glacial maximum, and also because the Glomar Challenger is located on the border between the Eastern and Western Ross Sea, and also because it joins the Pennal Basin at the head of the Hillary Canyon, which is also which works as a sediment drainage, but is also it's fundamental for the inflow and outflow of water masses related to the global overturning circulation. These are the methodologies. We adopted a multidisciplinary approach using sedimentological, micropaleontological, and also geochemical analysis. Okay, so this is the first core. Is one of the two collected closest to the ice shelf. And particular here you can see the change in the upper part of the core, particularly in the water content, the content of sand, silt, and clay, and IRD, and obviously the zirconium rubidium and also the magnesium over titanium, and the presence of sparse agglutinated foraminifera in this upper unit. This is the second core, and the second one collected close to the ice shelf. We have 4 dated intervals here, and the upper part is quite similar to the upper part of the core C04, but there is a change here between 119 centimeters and 200 centimeters. And is this level characterized by high water content, almost zero ice rafted debris, and lower values of the elemental ratio. Okay, this is the third core. This was collected at the margin of the Glomar Challenger Basin. And the carbonate foraminifera we recovered in this interval, or every test were recovered broken. So this could be could mean that they were transported. Okay, now we start to get close to the shelf break. And we can observe an increase in the sand and the HRD content in the upper part of the core. And the peaks you can see here in the magnetic susceptivity are caused by the presence of these large clasts. Okay, this is the last one. The collected. This is one collected close to the continental margin. Also, this core presents an higher content of sand and the ERD in the upper part of the core. This is probably due to the you probably have this situation because bottom currents may have removed the finer sediment. And we also use this core to test the XO25 analysis. This is a biomarker marker to highlight the presence or the absence of ice, or ice shelf or sea ice. And the green means the marker was the biomarker was detected, so we don't have ice, or at least we don't have a permanent ice cover in this part of the core. And we tested this analysis on this core in particular because it was collected halfway of all the other cores and other 3 box cores collected on the slope and rise area that I'm studying for my PhD project. Okay, so this figure is summarizes the distribution of these 3 units in the 5 cores. So we have the blue unit in the lower part, which represent the glacial environment. So this is mainly composed of and mainly represented by Micton. Then we have a glacial marine sedimentation, and the upper part is represented by open water sediments. So this might represent the Holocene sedimentation. And then we have this layer I've highlighted before. That according to these dates might represent a previous interglacial period. Or maybe it could be also another hypothesis could be also a plumite because of the fine sediment, or I don't know, also plumite. Okay. So to conclude, this the sedimentological, geochemical, and micropaleontological analysis helped us to identify these 3 units: glacial, submarine, and open waters. And the proximity of the Western Ross Sea and the proximity of the Glomar Challenger to the Penal Basin and the head of the Hillary Canyon makes the Glomar Challenger a crucial site to better constrain the evolution of the West Antarctic Ice Sheet. But also, obviously, additional analyses are required. In particular, we have planned to have the new AMS dates for each course, and other analysis of the XO25 marker are currently going on in these weeks. So thank you for your attention.
Thank you. Interesting talk. Okay, if you wouldn't mind, stop sharing, and then the next speaker, if you could share your screen. So
is that me there, Richard?
Say again, Jamie?
Is that me?
Yes, sorry. Yeah.
Yeah, good. All good. All good.
Yeah, no worries. Yeah, so next up we have Jamie Stutz, who's going to be talking about solid earth properties and ice loading histories in West Antarctica.
How are we looking there? You can hear me okay and
Looking
see
great.
the slides?
Yeah,
cool. Cool, thanks everybody. Yeah, so I'm Jamie Stutz. I'm a researcher here at Antarctic Research Center and Victoria University of Wellington, New Zealand. And yeah, just to start with a big thanks to everybody at SCAR for putting this on, and a special shout out to the conveners of this session for putting a really great order together. Following Alex and Carrie, I can really kind of dive into an overview of the project and maybe not get in too much into the detail of Cosmo or relative sea level records. I'd also like to acknowledge the collaborators on this project. It's growing, but basically this really started over a decade ago, and Mike and Terry thought it might be wise to look out for some glacial erratics as we're going around installing GPS sensors to bedrock. And yeah, so here we are. This image here from Lone Wolf Nunataks really lays out the motivation for this study. We can see the big honkin' power unit for the little antenna back there in the background. This is a PoleNet GPS station. But you can also see in the foreground, and then just littered around the entire Nunatak here, are foreign erratics, foreign rocks that are nicely perched on bedrock. And this is a situation that, as a glacial geologist, we always get really excited seeing these things. And really this juxtaposition kind of summarizes what we're trying to do, is a co-location of these ice load histories, these thickening and thinning profiles, as well as the modern GPS measurements of the bedrock there. And if we zoom out a little bit, these nice map and schematic from Pippa and others kind of highlights the existing network of PoleNet GPS stations there in the green triangles, and then the various geological records. So Alex talked about the relative sea level records, and Kari and I will talk about these ice extent geological records. So while this is really just a little bit out of date, a lot's happened just in the last few years since this is published. So we have some really great records from the Amundsen Sea embayment, as well as a really nice review paper recently by Richard and others, kind of outlining a lot of these concepts. And on this schematic here, we're going to be right in this area here. So looking in the terrestrial record, where we can pick up these kind of ice load changes, and then that measurement of the isostatic rebound. So really, we're just trying to kind of highlight the effort to obtain these records at PoleNet sites by the PoleNet field team, to really push ourselves to further understand the solid Earth properties. And that's where I say we're going toward that. We're not there yet. So if we back up a little bit, I'm the glacial geologist. Kari's already run us through this, but quickly, we've got exploding stars producing really high energy particles through the upper atmosphere of Earth and impacting the rocks at the surface, and creating new nuclides or isotopes within the crystal lattice of glacial deposits and bedrock. And a huge oversimplification here, if we're able to extract these nuclides, count them up, and with some knowledge of the production rate, we can back out this exposure age, which we then translate to the time that glacial deposit was dropped off by changing ice mass. And if we take this a little bit further, this is the classic kind of glacial dipstick model. And if we just take a cross section through a outlet glacier, we can see that, we've got our ice is starting to change. We've got the first erratic that is being deposited on this mountainside. The cosmic clock starts, and we've got our first point there on our thickness versus exposure age plot. And in this super simple case where the ice sheet just thins, we get this really nice profile of thinning through time. And of course, if we do that in a few sites around Antarctica, along the flow of a glacier, we get a little better at kind of reconstructing these sites, and ultimately the spatial footprint. So as Kari mentioned, this stuff can be doesn't really help with times where repeated cover has occurred and multiple episodes of burial. It also does not help with times that the ice sheet was thinner than present. This is kind of a re-advanced scenario. So this method really doesn't help us get at that, but still provides some really useful constraints for the kind of ice load history at a particular site, and that really can help us move towards understanding the solid Earth deformation. So as I mentioned, so there's the ice sheet depressing the continent, just a nice little cartoon. So we measure this rebound that's happening now with GPS. And of course, these are bolted to the bedrock. And the GPS is recording the total uplift. And the total uplift can be split into two components, the elastic, which is a little more immediate, instantaneous, if you will, versus the GIA, which is a more viscoelastic. And so we can, this can be supported with seismology, where basically we take the modern ice history, the elastic Earth model, and we can understand what the elastic uplift is. And so here's a map of all the GPS stations around Antarctica and the PoleNet network. And this is the total vertical bedrock. We can see a lot of action over in the Amundsen Sea embayment, where we're seeing a lot of ice mass change. And as I mentioned, we're going to need to remove that kind of more modern elastic component due to the modern ice mass changes. And Joey Durkin and others have done this in a pretty clever way using the cryosat altimetry, essentially over a decade. We're using this as our computed elastic vertical component. And basically we subtract this from our total to get the GIA or the viscoelastic component of the vertical bedrock. And you can see here this is still dominated by some of these rapidly rising areas around the Amundsen Sea area. And it's also really important here that the GIA, I mean, it kind of goes without saying that this is a really important set of feedbacks and processes that are used to determine the modern ice mass change from satellite data, as well as the ability to kind of constrain the Earth rheology. And as we talk a little bit more about this re-advance scenario, the rapid uplift of pinning points can actually be a huge process that can potentially alleviate some of the rapid retreat and thinning that may be predicted. So I'm going to quickly take you to 3 sites around West Antarctica where we've just kind of just started this work and are really interested to kind of watch it grow and kind of do a little bit more of this. So one site out here in the Clark Mountains in Murray Birdland, another site out here in the Bellinghausen Sea, the Lepley Nunatak, and then exciting new installation here at Mount Murphy. So we'll take you to Clark Mountains first. So what was really exciting about this site was the potential to tie in with one of the more important and kind of starter to this whole dipstick method was the Stone et al. Compilation from the Ford Ranges in Murray Birdland. And this really got the game started for this kind of terrestrial reconstruction using cosmogenic nuclides. And while during a site visit, maintenance visit in 2012, Terry made some stellar observations about some foreign erratics perched on some glacial bedrock, or glacially striated bedrock. And Klaus and I have extracted and calculated an exposure age. And if we kind of put that in a more regional context between these two nunataks in the Clark Mountains, we can see that those erratics that Terry picked up really fit well with this lowermost ages in the surrounding nunataks. And honestly, that just gives us good confidence that, so maybe we're not making a huge contribution here, but we feel like, hey, we can collect these samples, in a way that's meaningful for the geomorphologists, and then we can calculate exposure ages that are really relevant related to the kind of regional. Now, we'll contrast that with a really far-flung area here out of Lepley Nunatak, And this place, there's not a lot of rock sticking up. There's no work has been done, essentially unconstrained. And we've got a pretty good guess from the RAISE consortium there in 2014, showing lingering ice kind of still hanging around at about 5,000 years. And again, in 2012, Terry made some stellar observations, picked up some foreign rocks. Klaus and I have calculated, and we've only got 3 samples, but they came out pretty consistent. Somewhere around 10,000 years ago, we started to lose a lot of ice mass in this area. So again, kind of really adding value to the unconstrained portions of the continent. And the final one I'll mention here is this really exciting new installation on Mount Murphy. And if we back up quickly over here to this, this map from Barletta et al., this shows the predicted uplift from the GIA modeling that's constrained by the GPS sites. And in just a few short months ago, we were on the RV our own with Won Sang and Chung Ki and all the other folks on that cruise. Julia, we were waving hello to you. We managed to make a site visit to Bear Peninsula and get that back going again. It had been down for a number of years, so we kind of gave that some new life. And then we were lucky enough to make it over to Boyd Head here at the Mount Murphy, and we got to Chung Ki and others got to install this really new site. And if you'll see over here on the map, we're right in the center of this really high predicted uplift rate, and that's a really special site. So we're looking forward to a longer time series from that site, just to see maybe is that the highest uplift in Antarctica. Now, of course, as a glacial geomorphologist, I was there. I was happy enough to join the team in the field. And I made a nice vertical transect where I picked up a heap of granitic outcrop or granitic erratics that were perched on this lovely striated lavas at Boyd Head. So we're really excited about that, and I'll try to keep everybody posted on the results coming out of that. So there's further places where we're trying to do this stuff. So we've been lucky enough to have a field season in 2019 along the southern Transantarctic Mountains, and we've got a nice transect from Fishtail Point along the lower Skelton Glacier, and as well back there at Lone Wolf Nunataks along the upper Bird Glacier. And we're also really excited about a potential project, or the project that we're working on here out of Rockefeller Mountains, where we're utilizing rock samples that have been picked up over 30 years ago by some New Zealand researchers. So big shout out to the repositories around the world that can really help in this situation. And yeah, just a note there, PolNet has been sampling bedrock, and there are samples available from various GPS sites around the continent. So that's enough for me. Be happy to try to answer some of your questions. Remember, I'm a glacial geomorphologist, so I'll do my best there. And yeah, just a big shout out to all the institutes that support PolNet, support myself and the science. Thanks.
Thanks, Jamie. Really interesting project there, and looking forward to seeing how that develops. Now we'll move along to the next talk. If Gavin, you can share your screen. So continuing on from Jessica, Gavin Piccioni is going to be talking about dynamic record of ice sheet change on millennial scale cycles.
Great, thanks, Richard. Can everybody hear me?
Yep, all good.
Well, thank you all for being here today. And I also want to shout out the conveners for putting together a really, really great session. There's been some really cool talks so far. As Richard said, my name is Gavin. I'm a PhD candidate at University of Santa Cruz. And I will also be talking about a terrestrial record of Antarctic ice sheet response to these millennial climate cycles. So before I jump in, I will thank my collaborators on this project, Terry Blackburn, my advisor, and Slavik Tulacek, secondary advisor, as well as folks who gave us samples and I also have to shout out Anne Grunow in the Polar Rock Repository. Glad to see everybody's using the Polar Rock Repository. It's been a great resource. And then finally, NSF for funding this work. So my motivation for this talk will be very similar to Jessica's. So sorry for the reminders, but I will first give some background on the climate. This is the Epicodome C delta deuterium record, and throughout the past 250,000 years. And so I'm also looking at these Antarctic isotopic maxima, these millennial scale changes in Southern Ocean temperature with gradual warming and gradual cooling. And so there has been some background for how the Antarctic ice sheet has responded to these cycles that has done before our group, that's been done before our group. And I'll just highlight some of the offshore core people who have shown some Antarctic ice sheet response to these aims. So these two figures are from a paper by Weber and others in 2021, and they have these ice cores from the Weddell Sea. This is called Iceberg Alley because of the circulation of the Southern Ocean. Icebergs channel in Iceberg Alley, and you get these really nice long-term records for iceberg rafted debris there. And they're showing that you have uptick in iceberg rafted debris and therefore more icebergs during aims over the past 21,000 years. And so my work is trying to expand upon this by both doing a long-term or adding a long-term continuous record and as well as a terrestrial record, so we can really get at what glaciologic processes are causing this ice sheet response. So my samples will be a little bit different from Jessica's. These are, instead of crusts, these are subglacial precipitates that are accumulations. So they're about 3.5 to 7 centimeters thick, and they're being deposited along the East Antarctic ice sheet up against the Transantarctic Mountains. There was one question in the chat that asked how they're actually like being preserved over long periods. So these precipitates, for the most part, are found on supraglacial moraines where you have basal ice that is plucking them off the bedrock and bringing them to the surface. And they're probably not being transported over long periods of time or over long spatial regions. And so it's probably that they're just being plucked by the ice as the ice is moving in subsequent glaciations. And so the samples I'm looking at are these two here. You can see they're layered. These samples have dark to light layers, and the dark layers in both of these, black and orange respectively, are calcite. The white layers are opal. And so as a geochemist, this is sort of interesting because it must mean that you had these periodic back and forths of the subglacial chemistry to change the mineralogy of these precipitates. And so the first question I'm going to be tackling with this talk is simple. What causes these opal calcite cycles in the subglacial environment? And can we link that to any specific glaciologic processes? And so to answer that question, first, I want to make a time series that describes both the timing and the relative timing of these opal calcite transitions. And so to do that, I first started with this SEM image, and I am plotting an elemental map here from around this box. And this elemental map has silicon in blue, calcium in purple, so that those are our opals and calcite layers respectively. And then I take line scans across these images to plot these data spectrally. So this is calcium weight percent on the y-axis versus sample height. And you can think of high calcium weight percent as our calcites, low calcium weight percent as our opals. I then want to create time series, because again, we're interested in how these subglacial environments are changing with time. And so I dated as many of these layers as I can with U-series dating. Turns out the opals are pretty amenable to U-series dating. So we're able to make an age model across the samples. And so here I'm plotting for both samples those same spectra, but now versus age. And so you can see the sample here on the left, that one's being precipitated between 230 and 150,000 years ago. and the sample on the right is being precipitated between 54 and 42,000 years ago. So 100,000 years worth of time collectively with these samples. And a first order observation that we made was that the opal layers are occurring quasi-episodically, where in this sample on the left, you get an opal layer about every 10,000 years, and the sample on the right, you get an opal layer about every 2,000 years. And because, again, I'm thinking about these in terms of some climatological shift that's causing these perturbations of the subglacial environment, I plot them versus climate to see if there's any correlation there. So in these green curves, I am again showing ice core data. These are the Epicodome C deuterium record here on the left, and the Taylor Dome Delta 18O record here on the right. You could think about these for our purposes as temperature proxies, with these little peaks being the aims. So those are our millennial scale warm periods, and the valleys being the cold periods. And so the first main result that I find here is that when you have these aims in the system or in the southern hemisphere climate, that is when you get calcite layers. And it's pretty well correlated in both of these samples. Whereas when you're in a cold period, that's when we're precipitating out opal layers. So again, opal calcite transitions are correlating with these millennial cycles, with opal deposition during cold periods, calcite deposition during warm periods. And so for the rest of the talk, I'll be trying to call on a glaciologic mechanism to explain why we have these episodic shifts in the subglacial environment. And so the first data I'm going to present on that are chemical data. These are chemical elemental data extracted by laser ablation, and I did it across the sample. And so I'm plotting silica weight percent and calcium weight percent. Again, those are our opal layers that I've highlighted in gray, our calcite layers that I've highlighted in white. And the first proxy for subglacial chemistry I'm going to call on is the cerium star value. And really briefly, cerium star is basically measuring the relative abundance of cerium relative to the other rare earth elements. And the reason I want to know that is because cerium is redox sensitive. So in values above 1, in this case, you have more cerium than the other rare earth elements. Therefore, you're in a reducing environment because cerium is more soluble in a reducing environment. Whereas values below 1, you're in an oxidizing environment because in that case, cerium is more insoluble. It is not in the water column. And so if we plot cerium star for our layers, you can see a pretty nice correlation between high cerium star values and opal layers, low cerium star values and calcite layers. And so that's telling us that there's a shift in these waters that's happening to precipitate out these two types of layers. And it's probable that you have two separate waters that are precipitating out opal and calcite respectively. The second proxy I want to call on is the Delta 18O values from these samples. And I'm showing calcite in these light green squares. Opal values are dark green squares. Calcite values are light green circles. Sorry. So what we can take away from this is that the calcite values are systematically lower than the opal values, with calcite values down to -54 per mil and opal values up or about 8 per mil more enriched in Delta 18O. And this is also very interesting chemically for us. And the reason that is the case is has to do with the Delta 18O values of the ice itself. So I'm going to take you through, this is a map of the Delta 18O values of the modern ice sheet. And you can see that the lowest, most depleted Delta 18O values are in the middle of the ice sheet in the domes, and you get less depleted values around -35 to -25 along the edges. And so this is a big takeaway that we're calling on here, is that the calcite values must be coming, or the calcite waters must be coming from the interior of the ice sheet, because that is the only areas where you get glacial ice that is down to these -55 values. Whereas opals match pretty well with the edges of the Ross Sea, in terms of ice delta 18O values. And so this is the second result that I'm calling on, that calcite forms by the addition of oxidized meltwaters that are coming from the interior, and opals form from reducing waters that are probably coming from the edge. And so the mechanism I'm calling on here is that AIMs are causing interior waters to flush towards the edges. Whereas when you have a cold period, you're isolating these edge waters, and that's when you get opal values. So the last part of this talk, I'm just going to call on the glaciologic mechanism for what could cause these millennial shifts in the subglacial hydrologic system. And this is where I'm going to overlap again with Jessica's talk. And so what we did was we did an energy balance for the subglacial environment to try to say, how could you shift the hydrology on the ice bedrock, in the ice bedrock environment? And I'm going to gloss over this pretty quickly. I added this in sort of last minute, but in terms of getting a millennial scale shift in subglacial hydrology, there you can call on a few things. You can call on geothermal heating that might change the energy at the base of the ice sheet, but there's no reason why we would think that geothermal heating would change on these timescales. So we kind of disregard that. You could also call on a change in the amount of heat that's lost to the surface. And this gets back to a question I think that was also in the chat. Could these millennial scale shifts be a function of the thickness of the ice sheet, the accumulation rate possibly changing on millennial timescales? But the problem with that is that we are, based on where these samples are being found, they're likely being precipitated under about 1,500 meters of ice. And so to get a shift in the relative energy that is being lost or gained on these timescales would lag by about 10,000 years the actual AIM that is causing it. And so we don't think it could be accumulation rate that is causing these shifts. And so what we're calling on is shear heating. And when we model the modeled basal heat budget by shear heating, by changing thickness of the ice via a glaciologic mechanism, we're able to output changes in the basal heat budget that match in time our record. So in terms of that glaciologic mechanism that would change the shear heating on a millennial timescale, this is what we're calling on the Southern Ocean forcing, just like what Jessica was calling on. So in this case, what we have is during AIM events, you have more upwelling in the Southern Ocean. There are teleconnections between the atmosphere and the ocean that cause the Southern Ocean to upwell. And when that Southern Ocean water upwells, you get circumpolar deep waters that are warmer than the surface waters that are upwelling onto the continental shelf. And when these warmer waters interact with the ice shelf and the grounding line, they melt and eat at those ice shelves. And that melting causes a loss in the ice shelf buttressing effect. And models show when you melt back those ice shelves, you cause an acceleration of those outlet glaciers on the edges of your ice sheet. So again, this is a model by Gallage and others that model surface velocity on millennial timescales. And what we're calling on is that during cold phases, your ocean forcing is turned off, and you're isolating your edge waters and your interior waters away from each other. But during AIMS, your ocean forcing is melting at these ice shelves, causing your outlet glaciers to accelerate, which allows shear heating to open up these sort of capillaries between the interior and the edge of the ice sheet, which is eventually driving our precipitate record, where we get calcites during these AIM phases. So with that, I will finish up my talk, and I'm happy to answer questions in the Q&A, and thank you all for listening.
Great, thank you, Gavin. Fascinating research.
Thank you.
As he said, we'll have a Q&A session at the end of the next talk. So if you could stop sharing, Gavin, and then up next we have Jacob. So our last talk is from Jacob Anderson, who's going to be talking about ice dynamics during MAS 5 in the dry valleys and Ross Sea. Take it away.
Thanks, Rich, and thanks to all the conveners. This talk is part of my PhD research, and the image here is a view of Pierce Valley, which I'll be talking about for most of this presentation. So the nature of the problem, a lot of the research suggests that East Antarctica was largely intact during the last interglacial, and there was maybe perhaps a small amount of lowering in the Wilkes Basin, but no retreat. But one of the big questions is whether or not the Ross Ice Shelf was intact as modeled by Gollage and others, or in fact there was retreat followed by West Antarctic Ice Sheet as retreating after the Ross Ice Shelf. Challenges the records of the Ross Ice Shelf during this time are very poorly understood, as well as the terrestrial records during the last interglacial as well. And of course, this is an important analog for future warming scenarios as well. We know we lost parts of the West Antarctic Ice Sheet. The question is, how stable was the Ross Ice Shelf during that time, and the associated sea ice around that area as well. One of the interesting things is during the warm interglacial periods in the dry valleys, there has been an advance of the alpine and the outlet glaciers. So these glaciers almost act as a proxy for changing precipitation and changing conditions in the Ross Sea. The Taylor Dome records show there is an increased precipitation during these warm intervals, which causes this advanced question is, how does that moisture get delivered, and what does that mean for sea ice and ice shelf conditions? And like in the Ross Sea, the records are quite sparse and the time constraints are poorly resolved. So we went to Pierce Valley, which is an intermediate mixed zone, and we know that this site was ice filled during the last interglacial, and then later in the talk I'll also talk about Lower Right Valley, which is a coastal 4-zone site, which is a post-LGM site, so much younger, to compare and understand how sediments in the dry valleys have evolved through time. So the Pierce Valley drill site is the blue dot here. So we collected a 3-meter long permafrost core, as well as a series of surface exposure samples, which the context around exposure dating has been nicely talked about by the previous presenters, so I won't get into that. But we have a series of cobble granite samples which reveal minimum exposure ages of 65,000 years, which suggests that the ice sheet, that this lobe of Taylor Glacier, which had extended out during MAS 5, was still retreating during MAS 5A. So there was only perhaps partial retreat during that time. And a 2-isotope plot in the bottom left corner illustrates that these samples were in fact continuous exposure rather than having a complex exposure history, except for perhaps the older sample, which predates MAS 5E. And one of the interesting things about this site is these drift deposits, these cobble samples, are scattered amongst a series of fresh and reworked sediments. So you've got some much older, well-weathered samples hosting cobbles, these young cobbles, relatively young cobbles, peppered all over the surface. So this thin patchy drift is really a peppering of small clasts on top of a relic surface. So when that cold-based ice, non-erosive ice advances, It scatters some of these samples and then retreats, leaving the old surface behind. But we don't actually have a good understanding around the age of these relic surfaces. So if the assumption is that you've got these sediments with an inheritance, a prior inheritance, during the time of the deposition, you would have what you see in column A, effectively a straight line of well-mixed samples with a cosmogenic nuclide inheritance. At some time after that, there's and throughout the depositional history, there's cryotubation occurring in the upper surface, where there's sublimation and freeze thaw. So you get a mixing in that upper surface, which you can see in column B here, and that mixing then means that you get a uniform or relatively uniform nuclide concentration, whereas the dotted line, and then which you see below the paleo sublimation unconformity in C, continues to decay. So this is the post depositional nuclide production, which attenuates with depth. But in that upper layer, you've got mixing, so you still have this uniform concentration. And then if we go to column D, where we have a present environment, we've actually had a cooling, which has meant that the active layer has become shallower or thinned relative to its past. So the ice table is now above where it was previously. And so this is effectively what we saw with our data, and I'll explain that here. What we have is a Monte Carlo simulation, depth profile modeling that builds on previous depth profile modeling done by Alan Hiddy, where in that upper 65 centimeters, you can see a relatively straight line or uniform concentration of nuclides. And then at depth, you start to see that attenuation towards a modeled inheritance. So our measured samples are the black dots, which you can see. This is beryllium on the left, aluminium on the right, and the Monte Carlo simulation is the blue. This is the raw measurements. So what we found here was you have this mixed uniform layer in the upper 65 centimeters, and then you see this attenuation, but then there's a sawtooth below 200 centimeters, both in the beryllium and in the aluminium, and so this doesn't conform with an attenuation profile. But what we did was we assumed that mixed layer was reflective of that upper attenuation profile. So we averaged that upper 65 centimeters as one sample, and we removed the samples below 2 meters depth, as they were indicative of a previous event or an older surface. And when we removed those samples at depth and amalgamated the upper 65 centimeters, the modeled samples fit within 2 sigma of our measured concentrations. And so this allowed us to get and this is our amalgamated samples there. This allowed us to get age and erosion rate for these 2 sites. And interestingly, our depositional age of the permafrost predates MIS5, and the erosion rates are consistent with those. So we have the geological evidence of the cobbles at 65,000 years, sitting about 20 centimeters above the desert pavement, and our erosion rates are consistent with that if we extrapolated that. Of course, this also does include a period of ice advance, but this is a general assumption for the erosion rate since deposition. Okay, so based on the surface samples, the exposure samples that reveal Taylor Glacier advance happened during MAS5, which corresponds with increased ice accumulation in Taylor Dome. And our surface cobble chronology suggests that the retreat must have occurred at or before 65,000, perhaps during the MAS5/4 transition. We don't have any data after 65,000 years, but it's possible that retreat of the Taylor Glacier lobe continued after 65,000 until the LGM, where it was at its minimum, which is actually subsequently advanced since then. And our data support anti-phase behavior between the outlet and alpine glaciers in the dry valleys and ice extent in the Ross Sea. And this suggests a causal mechanism where cold-based glacier advance and retreat is controlled by moisture availability and drying due to sea ice and perhaps ice shelf retreat and expansion in the Ross Sea. Now, this hypothesis is speculative, does require further testing of temperature and atmospheric circulation in response to sea ice and Ross ice shelf retreat, but certainly interesting where we've got these increases in precipitation. Here's Taylor Dome here, increases in precipitation. After MIS5, where a lot of the marine evidence or a lot of the modeling rather suggests that it's been somewhat comparable to present conditions. So what is causing this increase in moisture availability and precipitation over Taylor Dome and allowing these glaciers to advance during this time? And just quickly, we also, this is the depth profiles from our lower Right Valley site, which is much younger, and it's effectively a uniform concentration that isn't really any different from the inheritance. But what it illustrates is that the deposits are young, but the sediments are old. Our two isotope plots of Pierce Valley and Lower Right Valley both show exposure burial histories of 1.2 million years. So these sediments have been recycled through multiple glacial cycles, but the depth profiles can be a new and useful tool for dating permafrost, and also really interesting to compare the age of surface drift, where there is this cold-based extension or advance and retreat. So just to summarize, the Pierce Valley depth profiles reveal surface permafrost deposits that predate MAS5. So they've been frozen and stable for over 65,000 and perhaps over 135,000 years. The presence of Taylor Glacier in Pierce Valley throughout MAS5 appears to be linked to prolonged interglacial conditions. During MAS5, we can't rule out increased precipitation over Taylor Dome during MAS5A caused a subsequent re-advance of Taylor Glacier, and that these depth profiles have a recent depositional history, but the beryllium and aluminium concentrations suggest the sediments have been recycled for at least 1.2 million years. Okay, thank you everyone, and we'll welcome any questions with the other speakers today.
Thanks, Jacob. Nice piece of work. Now we're going to move on to the final Q&A. So, just for the end of this particular session block, I'm sure you've all got burning questions to ask, so please put them in the Q&A. We do have one from a question for Gavin. This is from Julia. I'm curious about the Delta 18O data and interpretation of water having to come from interior of the ice sheet. Is there any fractionation in the minerals, and can that be different between the calcite and opal layers?
Yeah, thanks for the question, Julia. That's a great question. So in terms of the Delta O18, there is a large fractionation between the water and the minerals, and both opal and calcite have a different fractionation factor, and they're different by about 10 per mil. But these fractionations are very, very well studied experimentally. And so what we do is we are able to like correct for that fractionation between our measurements and what the inferred water composition is. So in terms of the Delta 18O, where generally we're at least confident that that is the Delta 18O of the water. But generally to your question about the interpretation of the water having to come from the interior, I have some other geochemical data for that I wasn't able to show today just from because of time constraints. But if you're curious, shoot me an email and I'd be happy to share any of this with you.
Muted myself. Thanks, Kevin. Julia has a follow-up question as well, if that's okay to answer. How much warm water is getting to Ross Ice Shelf or grounding line now? Is this mechanism that you've described for linking the ocean to ice behavior equally applicable to all outlets or only certain outlets?
Yeah, that's another really good question. So in terms of the warm water now, I would just call on some of the remote sensing data that shows that there is this active subglacial water system at the edge of the ice sheet now. Although I wouldn't exactly say that that's a perfect analog for our samples, because the remote sensing data that shows these ice sheets or this active flushing is happening every 10 years to 1 year, and we're showing these big events that are happening on millennial timescales. And so there's actually no evidence for what would be a larger flushing event. However, I do want to shout out, we have an undergrad who's doing some work on linking these active flushing events to these millennial scale flushing events in the subglacial precipitate samples. So that is something we are working on and are thinking about. But in terms of the modern analog, we don't really have anything for these like big flushing events, which would take the interior waters to the edge. But yeah, thanks very much for that.
Thank you.
Thanks, Gavin. A question for Andrea here from Ruthie. It's very exciting to see that you're reconstructing deglaciation patterns, especially ages, in this key area. What are your hypotheses about the curiously old ages at the site nearest the modern ice shelf? Andrea, are you there to answer that one?
Sorry, I forgot to unmute the microphone. Okay. So talking about the two ages in the lower half of the core, that might be due to that might be related to the previous interglacial period, so the mystery, or maybe a less exciting hypothesis that the two ages are due to reworked organic matter. And about the upper two ages, other older ages have been reported, particularly in the about the pelagic sediment. And according to Bart and Coney, this might be due to the erosion that might have stopped the sedimentation of pelagic sediment at some point. So we're trying to investigate even this aspect, adding new dates in all of the course, but also we plan to add at least other 2 or 3 days in this one to better reconstruct the edge model. Unfortunately, we don't have a box score to for the calibration, so we might have to be very careful during that part of the process to construct the edge model.
Great, thank you.
Thank you.
So I'll just say that we have gone over time. So I will just highlight that we have a poster session that's available throughout the whole length of the conference. So you can access those posters via the virtual platform. And we also have the second part of our session is going to be at the same time tomorrow when we have another great lineup of talks. And so I'll just say thank you to all of the speakers now. That was a great selection of talks, really interesting stuff. And there are still a couple of questions there which you are welcome to answer before you leave. But otherwise, I will see you all in the session tomorrow.
I see a question for me from Jacob. Is it cool if I answer that now?
Yeah, go ahead. You perhaps read it out as well, because I'm not sure everyone can see that question.
Okay, yeah. So Jacob asks, do you think the carbonate deposits around Lake Bonny could be used to investigate these processes during MIS5? That's a really great question, Jacob. Thank you. So I will say that there are a lot of pedogenic, like in situ carbonates in the dry valleys around Antarctica that are not a result of subglacial waters. And I expect that Lake Bonny probably are being deposited subaerially, maybe by glacial meltwater, but not necessarily by meltwater that is being delivered as a function of like a large scale glaciologic process. I don't know the specific carbonate deposits exactly, but I'd expect because of where they're at, they're not exactly the same as the precipitates that we're measuring. We go through like great pains to make sure that these samples are actually subglacial. And there are some chemical proxies for doing so, including the delta 18O and the carbon, because if the samples were being deposited subaerially, you would get atmospheric types of isotopic values, which we don't see. So good question, but I don't think so in this case.
Thanks, Kevin.
Kevin, I don't know if you can also see Roland's question that came in before that.
Oh, I don't.
Roland used the Q&A and.
Oh, I see.
Do you want to?
Oh yeah, that's a really good question. So yeah, I gloss over this, but the delta 18O values do change between the glacial and interglacial cycles, and the change is about 7 per mil. So if we were sourcing, say, glacial water during the opal layers and interglacial water during the calcite layers, that could definitely be why we're getting this discrepancy. This is something we've thought about. I think that my favorite sort of answer to this question is the fact that because we're seeing this over 100,000 years worth of time, we need this causal relationship, which is kind of a cop-out, I know, but I think that we're doing some work with folks who are doing this brand new type of delta 17O. So these are oxygen isotopes, and basically what these delta 17O oxygen isotopes can show us is whether we are sourcing glacial or interglacial water specifically. And the data that are rolling out of that are kind of telling us that we must be sourcing interglacial waters, which kind of makes sense because all these samples are forming during interglacial periods, and you wouldn't expect the residence time of the water between the modern and the base to be that long. to where you would take it between a glacial and interglacial type of ice. So it's definitely something where we are looking into, but yeah, to be determined. Thanks.
Thanks, Kevin. So I don't think we have any other questions. So thanks again to all of the presenters. And
Thanks,
we'll
everyone.
see you folks again tomorrow.
Yeah.
Thank you, everyone. See you tomorrow.